All right, recording has started. All right, this is our case study 5 presentation. My name is Sam Koscelny, and Maggie, if you want to introduce yourself.
Yeah, I'm Maggie Goodin.
All right, so we're going to get started on our presentation. If you want to go to the next slide, Maggie.
So when we first started with this assignment, we had to define all necessary libraries for not only reading the data, but performing all of the forecasting techniques that we will discuss in this presentation, such as moving average, exponential smoothing, and Holt-Winters. So a few of the most important packages were pandas, NumPy, and stats models. So first we started with a quick glance at the data. So in order to get the proper data, we had to use the slicing technique to get the data from January 2014 to September 2019. So as you can see in our code, we used the data from the negative 69th entry all the way till the end of the data to get that proper data set. And this is just a quick glance at the different parts of the data, such as the head, tail, and a quick description of the data. So the head is in the first image on the left and shows the first 5 entries of the data from January of 2014 till May of 2014. And then the second image shows the last 5 entries of our data set. And the last image on the right shows a brief description of how many data points are in our data set, the mean, standard deviation, and the minimum data point. And this is just a quick histogram of that data set. It seems that we have a central tendency around approximately 300 to 400 passengers. And as we saw in the previous slide, the mean was approximately 375 with a standard deviation of approximately 87 passengers. So this shows the time series decomposition of the data. We can see an increasing trend of the data from 2014 through 2019, and we can also see the seasonal peaks around the summer months for each year of the data, and that is shown in the third graph. We can also see the residual of our data. We can see that the points are spread pretty much evenly above and below the center line, meaning we have a pretty good random variation for our data. Now we're moving into the first forecasting method we used on our data set. And it was important in this section to use deseasonalized data to obtain our results. This is important because it gets rid of seasonality and allows us to compare the data from different years. In order to make comparison among data sets, you have to have deseasonalized data. So this was super important, especially with the moving average implementation. And this was also important for exponential smoothing. And Holt-Winters actually takes this into account itself and can work with seasonal data. So this is the graph of our moving average implementation with window size of 2, 4, and 8. So as you can see, all of them seem to match the data fairly well. But according to this picture, the one that seems to match visually is the moving average with window size of 2. So then we got the data spread out from the year 2014 until 2018 and found our seasonal index. And this is what we used to deseasonalize our data so that we could apply the moving average implementation to figure out what the best window size was to give us the best forecast. So after we had our seasonal index, we divided all of our data by that seasonal index and got the deseasonalized data for 2014, 15, 16, 17, and 18. And this is the results shown in our table. So next we had to move on to training the moving average model. So as you can tell, this deseasonalized data is very different from our seasonal data and has the new moving average windows applied over it. And once again, visually looking at it, you can see that the window size of 2 seems to fit our data best. And this was proven using the mean absolute deviation shown at the bottom of the screen. And as we can tell, the moving average with window size 2 has the smallest MAD, and so that was the one that we chose to test on the 2019 data. So then we had to test our moving average model. So the first line of code just shows us using this moving average with a window size of 2. So we're using the 2 previous years to forecast, or the 2 previous data points to forecast the next one for the 2019 data. Now in order to get this forecast, we multiplied our deseasonalized demand by the seasonal index that we obtained in that table that we showed previously, and use this for the 2019 data. So this graph shows our demand along with our forecast using the moving average of 2. And as you can tell, it seems to fit the data very well. in comparison with the other models. And so we determined that this was the best model to use for moving average. And so this was how we found the MAD for our moving average window size of 2. We used the same method that we did to find the MAD for the different window sizes of the moving average, and we got a value of 41.71. And this will be used to compare with the exponential smoothing model and the Holt-Winters model that Sam will discuss later to determine the best model for forecasting the data for October, November, and December of 2019.
Sorry, I was muted there. So after we did the simple exponential smoothing, after we did the moving average, we implemented the simple exponential smoothing. And so this is the code for that. You can see that we fitted a model to a variable called ES1, which is the exponential smoothing model. Next slide, if you can, Maggie. And then this is the rest of the code. And so, yeah, and then we regenerated the table for the exponential smoothing. So can you go to the next slide? And so that's the graph for that. So you can see that as exponential smoothing, as alpha is closer to 1, it more closely models the training data. And as alpha gets smaller, like in 0.05, it smooths out, hence the name exponential smoothing. Next slide, please. Okay, and then, yeah, so we used the smoothing levels of 0.05, 0.2, and 0.8 to fit all 3 models with the demand data. And so application of this forecasting method can be when the demand is expected to be consistent with past demand, using smoothing level of 0.8 as a reliable choice. And when demand expected to be considerably less, for example, due to supply chain issues, world events, or other issues, using a smoothing level of 0.05 might be an option to model a demand that does not go with the previous data. So yeah. And then so this is training the exponential smoothing model on the seasonal data. That is the code for, or no, we're applying exponential smoothing to deseasonalize data and determine the best alpha. So can you go to the next slide? And so after we deseasonalize the data, this is the model, the training data model. This is the training. This is the model on the deseasonalized data. Within it, found the most optimal exponential smoothing alpha, which is 0.82, which the computer found automatically. And so a discussion of the trained simple exponential smoothing on the deseasoned data is that seasonal data, first off, it's good to know what deseasonalized data is. So seasonal data is when the cycle structure repeats at the same frequency. In the last model, we saw that it did. So it kind of cycled in periods. And so in order to extract the most information from the data, it is good to apply deseasoning techniques to explore more trends in the data. So after training the model on the deseasoned data, we saw in the above graph that the repeating trend cycles were removed and there was more fluctuation in the data, and that the model is able to extract the optimal smoothing level for the deseasoned data, and it was overlaid on the deseasoned data in the above graph. And so this is addressing seasonality in exponential smoothing models. So that's the code for that. And then after we tested it, this is our test set for our tested model in 2019, when we forecasted 2019. And so the discussion of the tested simple exponential smoothing on the deseasoned data. So the previous graph showed that the forecasting technique using deseasoned data to train and test a simple exponential smoothing model in the original demand data. And as one can see, the model was tested on the 2019 year and took the best fitted exponential smoothing level, which was 0.82. And so by deseasoning the data, the repeating patterns in the data were resolved, thus the model was able to extract more useful information predicting future trends. And so our MAD score for the exponential smoothing model was 41.96. And next we trained a Holt-Winters exponential smoothing method. And so you can see that the hyperparameters we implemented in the Holt-Winters model were, we did the additive trend and the additive, seasonal, and then we implemented 12 periods for the 12 months in a year. And so that is the graph for the trained Holt-Winters model. You can see that Holt-Winters definitely followed the model very well when alpha is equal to 1.0 as expected. And so now we are testing the Holt-Winters model on the 2019 data, and this is our code for that. And so you can see in 2019, we trained the Holt-Winters model, and you can see how what it predicted the data to be. And so Holt-Winters model is best implemented when intending to capture seasonality in a data set such as this. And so after the model was trained, it was tested on the 2019 demand year and achieved good results, as seen in the next slide, which contains the MAD score for the model. The forecasted 2019 data used the Holt-Winters technique, followed the actual demand fairly well, especially in comparison with the MA, moving average, and exponential smoothing models. The MAD score for the Holt-Winters model is 24.23. And so now we implemented our final forecasting step, and we looked at the best MAD scores from all the models, and Holt-Winters won with a MAD score of 24.23. And then we forecasted demand for October, November, December of 2019 using our best model, which was the Holt-Winters, and you can see our demand for those months in the output. So conclusion of the winning forecasting model. So after the winning model was determined and it was trained and forecasted, the demand for October, November, December, one can conclude that this method of forecasting can be effective and determinative when trying to forecast data. It is often said that forecasting is never right, so it's essential to test multiple methods of forecasting to determine, the optimal model. And the process of training, testing, and evaluating different models of forecasting is a logically effective way to implement forecasting, and its effectiveness was exemplified in this problem. I think that's our final slide, so I appreciate you joining our presentation of our case study 5. Thank you.